Welcome to section 9.81, partial fractions. We'll take this over the course of 2 days, and this is basically the last section, the last skill of chapter 9 that we're going to work on, and perhaps of the class. So good job making this far. Congratulations. We've got just a little bit more to learn, and then that's it. We're going to close out this year. In order to explain what we're doing today, let me take you all the way back to, like, say, I don't know, 3rd or 4th, 5th grade. And we'll just talk about adding fractions. You know that when you add fractions, you need common denominators. You can't just say 1 over 7 plus 2 over 5. Like, you can't just add the 7 and the 5. You need to get a common denominator. In order to find that, often what you do is you multiply the denominator of both sides to get a common denominator, or at least common denominator. In this case, it's 35. So, and then you're going to multiply not only just the denominator but also the numerator to keep it an equivalent fraction. So you get 5 over 35 and 14 over 35. You get 19 35ths. That's the answer. Great. What no one ever did in 3rd or 4th or 5th grade, and we're going to start doing now, is reversing that process. If you started out with 19 35ths, could you somehow work backwards to get 1 over 7 and 2 over 5? Let me show you what that would look like. The process is called decomposing a fraction. And so if you started with 19 35ths, I guess our basic goal that you would have to work towards is something over 7 and something over 5. Knowing that 35 can be factored into 7 and 5, what number would that be, A and B? Figuring out is a little tricky. And so, but what we do know is that we could get a common denominator. Anytime you're adding fractions and you don't have common denominators, you might as well try and get a common denominator and see what happens. So you can multiply this fraction by 5 over 5 and this fraction by 7 over 7 to get what we see here. And I'm actually going to clear the denominator, multiplying all the terms on both sides by 35, and you just get what you see in the numerators here. Now, so 19 has got to be, so if you want to figure out what A and B are, then you have to choose a value of A and B that satisfies this equation. And we're just going to place on the restriction that there are no decimals or negatives. We're just looking for whole numbers. And so I guess I was trying to come up with a really good reason, and I couldn't figure out one aside from guessing and checking. You could just guess and check. You choose A to be 1, B to equal 2, and eventually it works. You could also graph it and see that it intersects right here and nowhere else. There's only one solution, and it is this, when if A equals 1 and B equals 2. So reinterpreting that in the original, you could say that 1/7 plus 2/5 is 19 35ths. We've reversed the process. Notice we started with 1 over 7 and 2 over 5 here, and we got this, and then we reversed it to go in this direction. And that's what we're going to be doing in this section. We are going to be reversing the process that we actually learned about in Chapter 1. Let me show you what that looks like. In Chapter 1, this is what we did. This is going forwards, like this, over here. We're going to be combining these fractions in such a way that first we need the least common denominator, and then we're going to combine them. We did this in Chapter 1, and this is what it looks like. Common denominator would be, but now what we're doing is we're doing it with variables. So common denominator of x plus 2 and 2x minus 3, there are no common factors between them, so we just multiply the two together, and that's what you get. So you multiply the first fraction by 2x minus 3 over 2x minus 3, and the second fraction times x plus 2 over x plus 2, and this is what you get. Now we have common denominators, and now we can subtract them. We can combine the numerators. So that's what that looks like here. If you if you distribute the top, FOIL the bottom, combine the like terms, notice these parentheses become incredibly important to your distribution. You have to make sure, especially here, a very common mistake is for students to forget that this is subtraction. They just forget to distribute properly, or they don't put the parentheses there, and if you don't use the parentheses, then you might mistakenly say this is plus, but it's actually minus. Combine the like terms, and eventually what you get is something like this, 4x minus 13 over that. So that's what we learned already in Chapter 1, and I hope you enjoyed this stroll down memory lane. We got 3rd and 4th grade, we got Chapter 1. So what remains to do is actually reverse this process. We're going to start out with this, and we're going to work backwards, and the answer will be this. And it's going to look something like this, only with variables. Notice we have two different variables here, so that's why the whole reason this is in chapter 9 in the first place and not chapter 1 is because we're going to, just to give you a preview, we're going to have multiple variables. We're going to come up with equations that have A and B and eventually C. So like we'll need to use our newfound skills in solving equations of solving systems of equations where they have multiple variables in order to figure out what A and B are going to have to be. So, starting with the purple now, instead of ending with the purple, here we go. Decomposing into partial fractions. So, you're given something like this, and a really great first thing to do in any of these problems is to factor if you can. This denominator looks like something you can factor. I like to use bottoms-up method. It's straightforward, and it gives me the answer the first time without guessing or checking. And then, so this is what we get. I'm going to factor this denominator into these two things. So, because the denominator factors into these two things, I'm going to put x plus 2 as my first fraction and 2x minus 3 as my second fraction. And so the answer is going to be some value of a, some value of b, that will make these two true. That will make this an identity, true for all values of x. So, just like I did up here, I'm going to try and combine these fractions with common denominators. You can see this denominator lacks a 2x plus minus 3, so I multiply here, and this denominator lacks an x plus 2, so I multiply this fraction by x plus 2. And now I have common denominators, and I can add them together. I'm going to distribute the a and the b, so I get these four terms. And now what I'm going to do is I'm going to factor out the x. Here's a strange technique you might not have anticipated. Two of these terms have x's in them and two of them don't, so I'm going to group them that way. I'm going to factor out an x from this term and this term, and this is where it is, and you can see that the coefficients are 2a plus b times x. And then these are the two terms that don't have x's. I'm going to group them here. So this is going to be kind of like the coefficient to my linear term, and this is going to be what my constant term is. The reason I'm doing that is so that I can compare very easily to what the numerator should be here. We have something times x, and that should be equal to 4x. And we have something over here, and that should be equal to negative 13. So what we can do is we can do a system of equations. 2a plus b has got to equal 4. 2a plus b, we're getting this by comparing the numerators. 2a plus b has got to equal 4, and negative 3a plus 2b has got to equal negative 13. So I've written them out, and now I have a system of equations. Like I said, the whole reason it's in Chapter 9 is that now we're able to really, in a very thorough way, solve these two equations. I decided to... since b is here, I'm going to use elimination. We just have one b out of all these four things. I think it's the easiest, best choice. So we're going to take this top equation and multiply it by negative 2 and add it to the bottom equation. When you do that, you get just this equation here. Like b times negative 2 is negative 2b, and you add it to this, you get 0. 2a times negative 2 is negative 4a plus negative 3a is negative 7a. And 4 times negative 2 is negative 8, and plus negative 13 is negative 21. Aha, this is an equation I can solve for a. I get a is equal to 3. Using a is equal to 3 in the original equation up here, I'm going to get 2 times, not a, but 2 times 3 is 6 plus b is equal to 4, so therefore b is equal to negative 2. Now that I know what a is and what b is, I can reinterpret it back in the first step that I did up here, or not first step, in one of the original. I know what a is, I know what b is, so then I can place it here. A is 3 and b is negative 2. So just for formatting reasons, you can say this is subtraction. My negative 2 is like this. Whew. That's a doozy. Those are big problems. Let's keep on going. Wow. Okay, so there's a lot of writing going on here. We're going to do another problem, and let me show you something that's new. Here, it already comes factored. Thank you very much, textbook. I appreciate you pre-factoring this for me. So you can see that 2x minus 1 is one of the terms here, and x minus 2 squared. Here's how we handle that. There are two different possibilities. There are two different. This could be factored into just x minus 2 or x minus 2 squared. When I say two different possibilities, you've got the most complex situation would be there would be a number here and a number here, and somehow they're multiplying up to get this. So you have to consider all the different powers. If this were a 3, if it was raised to the third power, you would x minus 2 squared, and then another term, d over x minus 2 cubed. If this were 2x minus 1 squared, it would be a over 2x minus 1, and then another letter over 2x minus 1 squared. So you have to consider all powers when you are trying to figure out what the numerators should be. This is the new thing. And of course, if flashing forward, you may have predicted this. If we have 3 different variables here, then eventually we're going to have a system of 3 different equations. Okay, so check this out. Now that we have a, b, and c all written out, we need common denominators. This denominator lacks an x minus 2 squared, so we're going to multiply numerator and denominator. Here, same thing. This denominator lacks a 2x minus 1 and a single x minus 2, so you're going to multiply both the numerator and denominator by just that. This fraction lacks a 2x minus 1 in order to get a common denominator, so we're going to multiply numerator and denominator by 2x minus 1. Now that we have common denominators, great, we can write one huge giant fraction with that common denominator. And I'm also going to start manipulating the numerators. This x minus 2 squared gets FOILed out like this. These two binomials get FOILed out like this, and I'm just recopying this for now. Then you can even distribute all the a to all the terms. Now we have 3 a's. Distribute the b to all the different terms. You got 3 b's. Distribute c to all these terms here. You got 2 different c's. Now I'm going to group them by quadratic term, linear term, constant term. Quadratic term, linear term, constant term. Notice I didn't exactly write this step out, but in order for all of this entire numerator to equal this entire numerator, we have to compare first let's compare the quadratic terms. Ax squared plus 2bx squared has got to equal 7x squared. So therefore, a plus 2b has got to plus 0. There's no quadratic term here. A plus 2b plus 0 has got to equal 7. Let's compare linear terms. In order for this to be an identity, negative 29 has got to equal negative 4ax minus 5bx plus 2cx. So, in other words, negative 2 has got to equal negative 4 plus negative 5 plus 2c. And that's what we see here. Negative 4a, negative 5b, 2c. It's got to equal negative 29. Compare the linear terms. 24 is here. 24 has got to equal 4a plus 2b minus c. And that's exactly what you see right here. System is 3 equations, 3 unknowns. It's definitely solvable. Convenient that a is already here. It's not like 5a or something. It's just a. So we're going to use that and to eliminate these 2 terms and bring them to 0. I see the negative 4, so I multiply the entire top equation by positive 4. 2b times 4 is 8b. 8b plus negative 5b is positive 3b. 0 times 4 is 0, plus 2c is 2c. 7 times 4 is 28, plus negative 29 is negative 1. Then I see this 4a, so I multiply the entire top equation by negative 4. Here, a times negative 4 plus 4a is 0. 2b times negative 4 plus 2b is negative 6b. 0 times negative 4 plus negative c is negative c. 4 times negative 4 is negative 28, plus positive 24 is negative 4. So that's the work we did getting zeros here. Next on the roadmap, I think technically we would have to divide this middle equation by 3. That's going to introduce a whole bunch of fractions I don't feel like dealing with. So I'm gonna get rid of this this negative 6b term first. So we multiply this by 2, and also I'm doing that. I'm further motivated to do this also because I can see that if I do that, I'm going to get something with the c's that I really like. Anyway, this times 2 is going to be 3b times positive 2 is 6b, and when I add that to this, we get 0 here. 2c times 2 is 4c plus negative c is 3c here. Negative 1 times 2 is negative 2 plus negative 4 is negative 6. Recopy the top equation. So, and recopy the middle equation as well. We get 0, 0, 0. That's nice. We get 3c is equal to negative 6. I'm going to divide the bottom equation by negative 3 to get c is equal to negative 2. Yay! So if c is equal to negative 2, I can figure out what b is in the middle equation. C is negative 2, so this is the middle equation, 3b plus 2 times what I know c to be, and I solve it, and I get b is equal to 1. And now that I know what b is equal to, if b is equal to 1, I can use that to find a. And I want you to figure out what a is by solving this equation. And once you know what a is, then you can interpret it into the original. This used to be a, b, and c, but now that I know that b is 1 and c is 2, I can rewrite it like this. This is decomposing functions. And if you wanted to check it, what you really could do is reverse the process again. You could recompose it. You could find the common denominator. You could add the numerators together, and you should get back the original. This right here. Here's another new twist. So, let's say that you wanted to decompose this nasty beast. First thing to do is definitely factor. Factoring the denominator, you can do using factor by grouping. You get x squared plus 1 and then x minus 4. We're not going to consider any imaginary numbers or complex solutions. So although if this were a different chapter or a different section, you could say that this is gets factored into i's. But we're not going to do that. We're going to leave it like this. So, and then you can also, did I factor the numerator? Where did I factor the numerator? I don't believe I factored the numerator. No, the numerator is not easily factorable. You'd have to use a quadratic formula, and it's just not helpful right now. So we can factor this into x squared plus 1 and x minus 4. So this should look familiar, and we don't have to worry about writing multiple. We don't have to worry about writing multiple of these because it's not squared. It's just to the single power. Like there's only one term, there's only one factor, and it's not being raised to the squared or third power. But one new possibility that we do have to consider is that it's not just a single number that is in the numerator, but there's also a possibility that you could have like 3x plus 1 in the numerator. Because of this x squared right here, because the denominator is quadratic, it has a degree of 2, then the numerator could have a degree of 1. And so therefore you need to allow for a linear term in the numerator, ax plus b. If this were x cubed, then you would have to write ax squared plus bx plus c. So if the degree were 3, the numerator could be as high as 2. So again, we have a, b, and c, and fast forward, it will be a system of 3 equations with 3 unknowns. But that's all right, because we can handle that. So we're going to get a common denominator for these two fractions and add them. So you can see here, x squared plus 1 times x minus 4 is the common denominator. And in order to achieve that common denominator, we have to multiply the first numerator and denominator by x minus 4. We also have to multiply this by x squared plus 1, x squared plus 1. So then now that we have common denominators, we can add them. I'm going to FOIL out this numerator, and this is what you get here, these 4 terms. I'm going to distribute this numerator, and this is what you get here, these 2 terms. Now we need to group. We're going to group by quadratic, linear, and constant terms. The coefficients on x squared would be a, negative 4, a, and c. Those are the quadratic coefficients, a plus c. The linear coefficients are going to be negative 4a and b. The constant coefficients are going to be negative 4b, not really coefficients, negative 4b and c are over here. So we group them by linear terms. And if this fraction is going to be, in fact, equivalent, if this is going to be an identity, then we need to figure out what a, b, and c are. Comparing the quadratic here, let me zoom out a little bit. Comparing this quadratic term with this quadratic term, a plus c has got to equal 1, because there's an invisible 1 right here. Negative 4a plus b has got to equal negative 17, because that's what that is. There's no c term. Negative 4b plus c has got to equal 35. So nice and convenient. There are a whole bunch of zeros here. Nice and convenient that there's a 1 here. This video is already long enough. I'm going to forego solving it in front of you, because I think at this point we've been doing quite a bit of practice, and so you should be able to eventually calculate that a is equal to 2, b is equal to negative 9, and c is equal to negative 1, and that's how the answer is like this, because you reinterpret a, b, and c back into what they were when we declared them up here. Wow. Okay, so I forgot to give you an audio check. It's 1992, The Silence of the Lambs. This is an amazing book-movie combo. It was first a book, then they made it into a movie, and people debate endlessly about which one is better in general, like book-movie combos. This is one movie that is absolutely amazing. It's an amazing book. It's an amazing movie. Best Picture. The actors Jodie Foster playing the lead female role, and Anthony Hopkins playing the evil, one of the easily top 5 evil villains of all time. He's up there with Darth Vader himself. There's really nothing in the Star Wars universe, and I'm a big Star Wars fan, that tops Anthony Hopkins in Silence of the Lambs. He's just an incredibly evil person. Gotta watch it. Psychological thriller. Check it out. 1992, Silence of the Lambs. Read the book. Tell me if you've seen it. It's super, super scary, super creepy, and maybe I've hyped it up too much already. That's your audio check. Start 9H1. So copy the first problem, do it, and I'll see you in class.